All right, here we go. So there was a question yesterday about the surface area of a sphere, and so if you don't know one of the formulas, simply just look it up online. So surface area of a sphere was, I believe, 4 pi r squared, and so stuff like that you can kind of keep in mind. We go to example 3. Our goal is to get through 3 examples today. 3 examples. Yes. Yep, yep, you'll catch along. So I instead of doing 3 examples yesterday, we just did 2 because I wanted you to be able to have a good shot at it. So we're going to jump around. We're going to do 3, 7, 4, and 9. So a right triangle has a base of 12 that remains constant while the height and the area increase. And again, I cannot say enough that I'm not doing any example that is simply just like, oh, we're just doing this because I find this interesting. All of the pieces I'm talking about are important and relevant to, number 1, you doing well in the test. Number 2, you being prepared for the AP exam. So there are nuances to every problem, and there's a reason why I show those. So right triangle's base of 12 remains constant while the height and the area increase. Areas increasing at a rate of 8 centimeters squared per second. At what rate is the height increasing when the area is 64 centimeters squared? Sounds like a ridiculous problem, correct? So again, my graduate work said if we divide things up using a graphic organizer, usually that helps us make more advancement with the problem than we would otherwise. So in this box, I like to model the problem. And I know that the triangle is getting bigger, correct? But I also know that the base remains the same. That's very important in this problem. What is the area of a triangle? 1/2 base times height. Now, what's different about this example is instead of having 1 variable, we have 2, correct? If you were to take the derivative, remember when you took the derivative of xy, you had to use the product rule. And so right now, if we took the derivative, we would have to use the product rule. However, maybe we can avoid that. We'll talk about the things that are changing in the problem, but the things that are also remaining the same. The area is changing. What is A prime? The area is changing at a rate of 8 centimeters squared per second. I also know that the base is 12. Is the base changing? No, the base is not changing. And this is key. In the last problem that we looked at yesterday, notice it said at what rate is the radius increasing when the radius is 5? Was the radius changing? Yeah, so we didn't plug the 5 until the end, correct? If something is not changing, you can go ahead and plug it in right away. So immediately what we can do with this problem is we can find where it is, and we can take this 12 and we can plug it in for the base right away. Is the height changing? The height is changing, and actually it says at what rate is the height increasing? So we're trying to find h prime. That is something that we don't know. We are told that the area is 64. Whether or not we really need that, I guess we'll find out. Okay? So I'm going to plug the 12 in for B because, again, the base is not changing. That allows me to plug it in right now. The area is equal to 6h. Is everybody okay with that? All right, so here we go. In this box, I take the derivative with respect to time of A equals 6h. Do you remember from yesterday what is the derivative of A? A prime. What is the derivative of 6h? 6h prime. So do we need to know the current area? No. Do we need to know the current height? No. None of it pops up in there, does it? Okay. So therefore, we have A prime, which is what? 8 is equal to 6h prime. Divide by 6, and we get 4/3 is equal to h prime. Or h prime is 4/3, and we need to get a label on this. Centimeters. Height is a single dimension measurement, so it's centimeters per second, whereas area would be squared, volume would be cubed. How's that? You okay? All right. Flip to problem number 7. Water is being poured into a cylindrical container at a rate of 6 cubic centimeters per second. If the radius of the container is 3 centimeters and the height is 6 centimeters, at what rate is the height of the water increasing? Sorry. When there is 24 cubic centimeters of water. Where would you start? What would you do? Draw a cylinder. Now what would you do? What's that? Okay, you labeled it. So it says the radius of the container is 3 centimeters. And the height of the container is 6 centimeters. At what rate is the height increasing when there are 24 cubic centimeters of water? Well, I need a formula for the volume of a cylinder. Close. Not circumference, but area of the base. So the volume is equal to the area of the base, which is pi r squared times the height. Uh-oh, I have two variables here. This is referring to the volume of the water, not the container. Think about the container. Is the height, or I'm sorry, think of the water. Is the height of the water changing? It is. Is the radius of the water changing? Why? Yep, the water is going to assume the shape of the container in that situation, right? So we know that the radius of the water is always 3. We are trying to determine what? H prime. Are we given V prime? 6. So because the radius of the water is not changing, I can take that 3 and drop it right in there. Volume is equal to 9 pi h. Derivative with respect to time of V is equal to 9 pi h. What is the derivative of volume? And what is the derivative of 9 pi h? Nine pi h prime. Do we need to know the current height? Do we need to know the current volume? None of those things are important at this moment. V prime is 6 equals 9 pi times h prime, which we're trying to determine. Divide both sides by 9 pi. I get 2 over 3 pi is equal to h prime, where h prime is 2 over 3 pi. What is my label? Centimeters per second. Again, think of what you're measuring. You're measuring height. Height is a single dimension measurement, so we just have centimeters as opposed to centimeters squared. So the only change to these two problems is that we had multiple variables. And it said, hey, we'll probably have to use the product rule. Except we were able to avoid that, weren't we? We were able to avoid that because we saw that something never changed in the problem. We flip back to problem number 4. This problem is at the heart of what you're going to need to be able to do in the second level of problems that you're going to engage in today. It's going to be a little bit more challenging. The volume of a ball is increasing at a rate of 10 cubic centimeters per second. So I have a sphere. Oh, is that... Okay, Bailey's laughing at me. So is Sydney. Thanks. Appreciate that. I'm trying to give it depth. So it's increasing. So this is getting bigger. So what are the things that are changing then with the ball? The radius, the area, volume, diameter, circumference, all that's changing, right? There's really nothing that's staying the same. It's all changing. Do I have a formula for the volume of a sphere? Four-thirds pi r cubed. We're given V prime. V prime is 10. We're also given V. The current volume is 100. What are we looking for? Diameter. Diameter prime, right? The rate at which the diameter is changing. Oh no, what's the problem with that? You don't have anything that speaks of diameter. You're like, well, just double the radius. Doesn't necessarily work like that. Can you tell me the relationship between R and D? The radius is half the diameter, correct? So just understand that some people write equations that involve R. There's no rule that says we can't write an equation with D, right? For example, circumference is equal to 2 pi r. Or you could write circumference is equal to pi times the diameter. Those are the same, right? One's written in terms of radius, one's written in terms of diameter. Let's just make up a new equation. Just plug 1/2 the diameter right in for that guy. So we have volume is equal to 4/3 times pi times 1/2 d cubed. If we chose to take the derivative in this situation, we would have to use the chain rule. So let's write it so it's not involving the chain rule. What is 1/2 cubed? 1/8. And 1/8 times 4/3 would be 4/24. 4/24 is 1/6. So it looks like we have volume is equal to 1/6 times pi times d cubed. So because the problem is asking for diameter, I find a way to insert diameter into the equation. Now, you're never going to see that written in a textbook, but they sure could have decided to do that instead, right? So let's take the derivative with respect to time of volume equals 1/6 pi d cubed. See if you remember how to do this. What do I get? Rachel is 100% correct. V prime is 1/2 pi d squared d prime. Is there any question how we got that? You all good? What is V prime? 10 equals 1/2 times pi. Do we know the current diameter? No, we don't, do we? D squared d prime. Could I figure out the current diameter? What's that? So we drop the 3 in front when we take the derivative. How could we find the current diameter? Use the volume, right? If we know the current volume is 100, we could plug in 100 right here and solve for D, right? So I'm going to have to do that. 100 is equal to 1 over 6 pi d cubed. That will allow me to find the diameter. I multiply by 6, 600 equals pi d cubed. Divided by pi, 600 over pi is equal to d cubed. I'm going to figure out what that is. Fortunately, I have a calculator. It seems to work pretty well. 600 divided by pi. And I'm going to find the cubed root of that. I like to take things to the 0.33 power. That's kind of how I operate when I get that kind of stuff. 5.75, we'll go 5.76. Are we okay with that? So I did a little side work here to find out that diameter is equal to 5.76. Now I can make use of that. 10 equals 1/2 pi times 5.76. Got to square that times d prime. I have to my calculator to work this through the rest of the way. 10 divided by 0.5 is 20. Then I got to divide that by pi, and I get 6.36. And I got to divide it by 5.76 squared. And I get 0.19. D prime is equal to 0.19. What is my measurement? Centimeters per second. What do you think? A little bit more involved? I want a question. Okay, we're gonna save the more challenging problem for tomorrow. We'll see what we do on Monday and Tuesday, and I might have a day to kick around here or there, but we'll see what we can play with. This is a nice one. Boyle's law. Are people familiar with Boyle's law? Okay. Boyle's law states that temperature in gas, okay, if the temperature of gas remains constant, then the pressure and the volume of the gas satisfy the equation P times V is equal to C, where C is a constant. Okay, so the idea is that if you decrease the volume, okay, the pressure is going to increase, right? And if you increase the volume, the pressure will decrease. So you just think of a balloon. If you were to squeeze that balloon and decrease the volume of it, eventually it might pop because the pressure will then increase, right? As one goes up, the other one goes down. So if the volume of something is decreasing at a rate of 10 cubic inches per second, how fast is the pressure increasing when the pressure is 100 pounds per inches squared and the volume is 20 cubic inches? Oh boy, looks challenging, right? Say what you just said. Say what you just said. How do you draw it? And you don't. What you do is sometimes you don't really have a picture, but you start to model what's happening with the problem, okay? What you do is start to model what's happening with the problem. So let's see what's happening here, okay? It says when the pressure is and the volume is, okay? See that? So we have P times V is equal to C. What is the current pressure? 100. What's the current volume? 20. If we multiply those, we get 2,000. Everybody good? Suppose the pressure was reduced to 50. What would happen to the volume? It would go up to what? 40. Because the constant doesn't change, correct? That's the law. So we have our equation. I just modeled like what's happening. As the pressure goes down, the volume goes up. So I have an understanding of the problem. P times V is equal to C. Tell me, What's changing in the problem? Is pressure changing? Yes. Is volume changing? Yes. Is the constant changing? No. So we have things like P, V, P prime, V prime. We have C. You know, C is 2000. What else do we know up here? What's that? We know the volume is what? 20. What else do we know? What is the pressure? Pressure is 100. What else do we know? What's that? Close. -10. It is decreasing. Would you agree we're looking for P prime? If P is changing and V is changing, then we have to make sure that those stay within our problem right now. And watch what happens when we take this derivative. We're going to need to use what? The product rule. Take the derivative with respect to time of P times V is equal to 2000. I use the product rule. What's the derivative of P? P prime times V plus PV prime is equal to 0. Some of you on your test made the mistake that when you did implicit differentiation on your last test, you took the derivative of, I think there was a 9 on the end here, you listed the 9. I've seen some smiles. Sorry if that got you, but the derivative of the constant is 0. I can now plug some of these pieces in. I don't know P prime, but I do know V. What is it? So I have 20 P prime plus, what is P? 100 times -10. Or 20 P prime is equal to 1000. Divide by 20, and P prime is equal to 50. 50 what? So if you look at pressure is measured in pounds per inches squared. And then it's with respect to time, right? So you have to have a time label on the bottom. What's our time? Seconds. So you can just attach the seconds in the denominator. So you saw an example that involves the product rule. That's enough for today. But in case anybody watches the video, I want to show you on your homework what you can do so far. What I think you would have great success with. Problem 1, 2, 3, 4, 5, and 6. Nobody should show up tomorrow without problems 1 through 6 done. Those should all be straightforward. You shouldn't have any problem with them. Maybe you'll have a question or two, but we should be able to work through them rather quickly. Problem 7, I already had you start working on that. That's definitely a go-getter right there. Okay? This one is tough, but you can do it. Okay? It's tough, but you can do it. You can definitely do 10, 11, and 12. Don't do 8 yet. You can go ahead and try. That's what we'll start with tomorrow. But if you want to be at your best tomorrow for attempting problems like 8, then we need to have a strong foundation for this. Got to have some things figured out. Got to clean up the little mistakes that we're making. So, all right.